Hi everyone, I hope you had a great spring break. Hera and I had a nice time. I wanted to talk to you about a couple more topics that we need to go through before we've hit all the topics that are on the AP exam. So there's a few more topics that typically we would hit in the last couple units of the semester, which aren't on the AP exam. But some of the basic ideas of those topics are assumed as prior knowledge from first year chemistry, and so they are on the AP exam. So one of those topics we're going to talk about today, which is titration, and then we're going to talk about the other two, which is redox reactions, later this week. So let's get started. Go ahead and take a minute to answer these three questions. Pause the video, answer the questions. We'll go over them. Okay, so sodium hydroxide and hydrochloric acid are going to react in a double replacement reaction. We've talked about how a double replacement reaction often forms an insoluble product. In this case, it's not forming an insoluble product. It's going to form NaCl, which is soluble, and then the other product would be HOH. That's water. It's going to form water, right? The net ionic equation here, we're starting with H plus, Cl minus, Na plus and OH minus separate from each other, right? We're going to end up with Na plus and Cl minus separate from each other, right? Aqueous sodium chloride is really just separate ions, but water is not, right? When H plus and OH minus come together to form water, they form a real chemical bond and they don't dissociate, they don't break apart. So the net chemical equation here is H plus OH minus making H2O. Cool. If we look at the second example, right, we've got iron 2 hydroxide and acetic acid, right? That's going to form a double replacement reaction as well. The anion here is going to go with the cation here. The cation here is going to go with the anion here. This is written a little funky, but the anion here is acetate, C2H3O2, right? And then essentially the cation here is H plus, right? And so we're going to have this reaction where the iron reacts with the acetic acid, and we're going to make iron 2 acetate and water as well. Cool. The net ionic equation here, we're starting with acetic acid, which is a weak acid. So this mostly doesn't dissociate to start with. That is going to, the H plus from that is going to bond together with the OH minus from the iron hydroxide. And so essentially the acetic acid is going to lose its H plus, the H plus is going to bond with water, and we're going to have a leftover acetate ion. Cool, and then if we look at the third example, we've got phosphoric acid reacting with calcium hydroxide, right? So there's our balanced chemical equation. You have to be a little bit careful about the coefficients, right? You need a 2 in front of H3PO4 and a 3 in front of calcium hydroxide. In order to balance out, you're going to end up with 6 waters. And then if we're looking at the net ionic equation, again, we have a weak acid. So H3PO4 starts with the hydrogens attached to the PO4. That's going to react with the calcium hydroxide. It's going to react with the hydroxide from the calcium hydroxide, right? Calcium hydroxide starts out dissociated. So we essentially start with just OH minuses. Calcium is just a spectator this entire time. The OH minuses bond with the H pluses to make water, and we have a leftover phosphate ion. And it's worth noticing that all 3 of the hydrogens from H3PO4 are going to react. That's true for any acid that has more than one hydrogen. If you react it with a base, the reaction between H plus and OH minus to form water is a very, very strong reaction. It's very exothermic. And so that essentially goes to completion. And so your acid is going to lose all of its hydrogens. Your base is going to lose all of its OH minuses. Cool. You might notice that all 3 of these reactions are reactions between an acid and a base, right? That's what's called a neutralization reaction. And the basic idea, in a neutralization reaction is you have an acid and a base. You can see that all of these reactions make water, and then they all make some sort of leftover ionic compound that just has the 2 ions that were the the conjugate acid and the conjugate base of your acid and base. So the basic formula for a neutralization reaction would be an acid plus a base, mix water and some sort of salt, where we're using the word salt loosely to mean any sort of ionic compound. So let's go ahead and do a little practice, right? So how many milliliters of 0.25 molar NaOH solution are needed to react completely with 25 milliliters of 0.150 molar HCl solution? Pause the video, solve it on your own. My cat is waiting for you to solve the problem on your own. All right, let's go through this. It always helps to write out the balanced chemical equation beforehand so that you know the stoichiometric ratio of acid to base, right? In this case, it's a 1-to-1 ratio, but that's not always true, as we saw on the do now problems. Cool. What you're gonna wanna do is figure out the moles of whatever you can figure out the moles of, which in this case is the acid, right? For the acid, we know both the volume and the molarity. For the base, we only know the molarity. So for the acid, we can figure out the moles of acid, right? We can do that by converting from milliliters to liters, right? And then the molarity is really a conversion between moles and liters, right? It's telling us there's 0.15 moles per 1 liter. So once we convert to liters, then we just multiply times 0.15 moles per liter to get the moles of HCl. Then we can do some stoichiometry. In this case, the stoichiometry is pretty simple, right? It's a 1-to-1 ratio of acid and base. So however many moles of HCl we have the same moles of NaOH. And then if we know the moles of NaOH and we're given the molarity, we can calculate the volume, right? So we just do the moles divided by the molarity to get the volume. And so we get 0.0150 liters of sodium hydroxide is required to neutralize that HCl. So we can see that we can use essentially stoichiometry to relate the amount of acid in a reaction and the amount of base in a reaction. And we will often do this in the lab. Most commonly, we'll do that when we're actually solving for the concentration of an unknown either acid or base, right, whose concentration we don't know. And we can do that using a process called titration. So the idea behind titration is it's a lab technique for determining the concentration of dissolved substances. And so what you're gonna do is you're gonna have a standard solution, the titrant, that's a solution whose concentration you know, and then you're gonna react that with a solution of unknown concentration. And you're gonna keep reacting until you hit the equivalence point. The equivalence point is the point in the titration where the concentration of the acid is equal to the concentration of the base. And at that point, you've added an indicator, and your indicator is gonna change color. And that's your signifier that you've reached the equivalence point or the end point, which is when the indicator changes color. So ideally, the equivalence point and the end point should be the same, right? You should have an indicator that changes color when the concentration of the acid equals the concentration of the base. In practice, those are actually usually not identical because most of the indicators that we use don't actually change color at a pH of exactly 7. And so you can select an indicator that's going to change color near that pH, but it's usually not exactly at that pH. And so when you end your titration, you're pretty close to the equivalence point, but you're actually not exactly at the equivalence point. Cool. Let's look at an example of a titration reaction. We've got our acid of unknown concentration. I'm going to add a very specific amount. You can see in the video they're using a burette, and this is like the very tip of the burette there, to measure out the exact amount. Burettes are one of the most accurate ways of measuring out a volume. Okay, they're adding an indicator. Most commonly use phenolphthalein, right? That's clear in acid, but it turns pink when it's in a basic solution. We've got a base whose concentration we know, right? So this is a base with 0.1 molar. We know the concentration of the base. We're going to add it to the burette. And then we're going to start adding it to the acid. And what you see is that as you add the base into the acid, the indicator changes color, right? The phenolphthalein is turning pink. But then as they swirl the acid, that pink disappears. Which is because the base gets neutralized by the acid, right? So like when you have a little drop of base right here, briefly that bit of the solution is basic, but then as you mix in the acid neutralizes, so you end up with an overall acidic. And so what we're looking for is we're adding NaOH until the solution transitions from being acidic to being basic, right? And when the solution transitions to being basic overall, it's going to stay pink permanently. It actually takes a while, so I'm gonna like jump ahead and slowly. There we go. And as you saw in lab, it's tricky to actually stop this in exactly the right time. There we go. Okay, so the pink is staying, it's not disappearing. That's the end point of our titration. Ideally, at the end point, right, we can now measure the amount of NaOH that's been added. We know the concentration of the NaOH. And so from that, we can calculate the concentration of the acid. Awesome. Okay, so from our titration experiment, you're going to react either an acid of known concentration with a base of unknown concentration, or a base of known concentration with an acid of unknown concentration, right? You can measure the volumes of both. You can see when the reaction is completed, when the moles of acid equals the moles of base, because the indicator changes color. So you have that visual cue, you can stop it, you can measure the volume of each, and from that you can calculate the unknown concentration. We've done a little bit of that math already, right? The math is the same as what we've already done. It's just basic stoichiometry. If you want a little bit of shorthand, right? I don't think this calculation was that long, but if you want to abbreviate it even more, you can notice that in any acid-base reaction, the essentially net equation is H plus and OH minus forming water. And the moles of H plus always has to equal the moles of OH minus. And so if we want to sort of shorten this calculation just a little, we can abbreviate it by saying, okay, well, the moles of H plus has to equal the moles of OH minus. It's fine. To get the moles of H plus, we do what we did here, right? To get the moles of H plus, that's equal to the volume times the molarity, right? And to get the moles of base, that's also the volume of base times the molarity of the base, right? So the moles of H plus would be the molarity of H plus times the volume of H plus. The moles of base would be the moles of OH minus would be the molarity of OH minus times the volume of OH minus. For a monoprotic acid like HCl, right, cool, you just do the molarity of HCl times the volume of HCl. If you have a diprotic acid like H2SO4, right, the molarity of H2SO4 would be twice as much as the molarity. Sorry, the molarity of H plus would be twice as much as the molarity of H2SO4, right? For every one H2SO4, there's 2 H pluses. So you would need to multiply the molarity on the bottle by 2 to get the molarity of H plus. Cool, let's go ahead and use this in some examples. Take a minute, pause the video, see if you can answer these example questions. We'll go over these in a minute. Okay, let's go ahead and take a look at these example problems. So in the first problem, we're titrating some NaOH of known concentration with HCl of unknown concentration. So we can go ahead and use the titration equation, where the molarity of acid times the volume of the acid is going to equal the molarity of the base times the volume of the base. The molarity of OH minus we know is 0.45 molar. The volume we're given is 83 milliliters. They tell us the volume of acid, right, 235 milliliters. We don't know the molarity of acids, we're solving for that. It's worth knowing, right, if you wanted to know the moles of OH minus, you would have to convert this milliliters to liters.
by dividing it by 1,000, right, in order to get the moles, since molarity is moles per liter, not moles per milliliter, right? But on this side, if we wanted the moles of H+, we would also have to divide by 1,000. So if we're dividing by 1,000 on both sides, that factor ends up canceling out. And so it turns out you can use volume in whatever unit you want, as long as you use the same unit on both sides of the equation. So the milliliters here doesn't need to match the unit in the molarity, moles per liter, right? That doesn't need to match because this milliliters is really canceling out with this milliliters. So this unit just needs to cancel out with this unit. Cool. Okay, so we can just do this directly. No need to convert to liters, right? The molarity of the acid is just going to be 0.45 times 83 divided by 235, which is going to give us 0.16 molar acid. Cool. The next question is a little bit more conceptual, right? So the idea is you're titrating an acid into a base and you allow some extra drops of acid to fall in. And we want to know how that's going to affect your concentration of the base. Cool. Well, in this situation, we've added like more acid than we're supposed to, right? And so we're going to think that it took more acid to neutralize the base than it actually took. And so because we think it took more acid, that means we're going to think our base is more concentrated than it actually is. Right? We can explain that conceptually, or we could also explain that in words. We could also explain that in using some math, right? If we look at our equation, where essentially what's happening is we've increased the volume of the acid without changing the molarity of the acid, right? We haven't changed the volume of the base that we're titrating into. And so if we increase the volume of the acid, what that means is in our calculation, the molarity of the base must also increase. And so it's going to look like our base is more concentrated than it actually is. Our final result for the molarity of the base is going to be too high. Cool. In problem number 5, we're titrating NaOH and H2SO4. So we can still use this equation, molarity of H plus times volume of H plus equals molarity OH minus times volume OH minus. The molarity of the acid we're not given, that's what we're solving for. We know the volume is 155 milliliters, right? The molarity of the base we know is 0.75 molar. We know the volume is 38 milliliters, right? We don't know the molarity of the acid. And in fact, the question is asking us for the molarity of H2SO4, not the molarity of H+, right? So if you think about H2SO4 is going to break off into 2 H pluses and 1 SO4 2 minus, right? So the molarity of H plus is going to be twice as much as the molarity of H2SO4, right? And so instead of writing in molarity of H plus, we're actually trying to solve for the molarity of H2SO4. But the molarity of H plus is equal to 2 times the molarity of H2SO4, right? Because there's 2 hydrogens for every mole of sulfuric acid, 2 moles of hydrogen for every mole of sulfuric acid. So we're going to do twice the molarity of H2SO4 to get the molarity of H plus, right? So it's worth noting, anytime you have a diprotic acid, right, you have to multiply the concentration times 2 in this equation, right? If we had a diprotic base, we'd multiply that concentration times 2. Cool. Okay, so the molarity of H2SO4, which is what we're solving for, right, is going to equal 0.75 times 38 divided by 2 times 155, which if you actually plug that into a calculator is going to give you 0.092 molar H2SO4. Good. The next question, question 6, is another conceptual question. Right. So we've left a couple of drops of water in our burette. This is bad lab practice. And we're filling the burette now with base and titrating that into an acid. So what's going to happen is the water that's in the burette is going to dilute the base. But we don't know that the base has been diluted, which is a problem for our calculations, right? So because the base has been diluted, we're going to have to add a larger volume. We're going to end up adding an artificially inflated volume of that base. Larger right? We're going to add a volume that's too large into our beaker of acid, right? And so because we've added a volume that's too large, it's going to make it seem like the acid is more concentrated than it really is, right? So it makes the acid seem more concentrated. Again, based on this molarity equation, right, MHVH equals MOH what's happened is we've artificially inflated this volume of hydroxide. In reality, what's happened is this has gone up and this has gone down, right, and they've canceled each other out. But we don't know that. When we're putting that into our calculations, we're going to plug in a molarity for the base that's equal to the molarity that our jar is labeled with, right? If the jar says 0.1 molar, we're going to plug in 0.1 molar because we don't know that the burette has water in it that's diluted our base. And so in reality, this has gone down, but we don't know that. So when we're doing the calculation, this is going to stay the same. This is going to go up, right? This is just given. It's however much acid we stick in our beaker, right? If this goes up, we're then going to overestimate the molarity of acid. And so we're going to end up with a molarity that is too high. That's why it's important when you're using a burette that you actually rinse the burette with water, but then after you've rinsed it with water, you rinse it again with the titrant. So if you're trying to titrate base into your acid, if you're trying to titrate sodium hydroxide, after you've rinsed the burette with water, you need to rinse it with a little bit of sodium hydroxide. And you ideally should actually do that a couple times so that the little droplets that are remaining aren't water, they're actually droplets of the same concentration of base that you're about to add into the burette. So that way you can avoid that source of error. Good. Okay, let's look at our last problem. So for the last problem, problem 7, right, they've given us some H3PO4 that's reacting with barium hydroxide. It might help to actually write out the chemical equation for what's going on. So we've got H3PO4 reacting with barium hydroxide. That's going to make barium phosphate, which if you use the crisscross rule to figure out the formula, right, phosphate has a charge of 3, so we give barium a subscript of 3. Barium has a charge of 2, we give phosphate a subscript of 2, right? So the charge of each is becoming the subscript of the other. And then, of course, that's going to make water. And if we want to balance this, we can see, okay, well, there's 2 phosphates over here, so this is going to need a coefficient of 2, so that we have 2 phosphates. There's 3 bariums, so this is going to need a coefficient of 3 for the bariums. Okay, now we've got 6 H pluses. Oop. This is barium hydroxide, that's BOH2. We've got 6 H pluses reacting with our 6 OH minuses. That's going to make 6 waters. So that's our balanced chemical equation for what's happening. You can do some stoichiometry in this problem, or you can just use the molarity equation, but it's worth realizing, right, this is diprotic, this is triprotic, and so that's going to affect our calculations. So cool. So the molarity of H plus times the volume of H plus is going to equal the molarity of OH minus times the volume of OH minus. The molarity of the H3PO4 is 0.3 molar. We're given that in the problem. But for every mole of H3PO4, we get 3 moles of H plus. The molarity of H plus is really this times 3, right? Because we get 3 moles of H plus for every mole of H3PO4. So it's really 3 times 0.3. And then the volume would be 12.5 milliliters. That's equal to the volume of base, which we know we're given that's 285 milliliters. What we want is we want to know the molarity of barium hydroxide of BaOH2. The molarity of OH minus is equal to the molarity of barium hydroxide times 2, because for every barium hydroxide, there's 2 hydroxide ions. The molarity of OH minus is twice the molarity of the barium hydroxide. So we've got 3 times 0.3 times 12.5 equals 2 times x times 285. Okay, so we can solve for the molarity of the barium hydroxide by doing, what is this, 3 times 0.3 times 12.5 divided by 2 times 285, and we're going to end up with 0.8 and you get like 0.0197, but we're rounding to 2 sig figs, so that's going to round to 0.020 molar.
Cool. Now that we've gone over some basic titration calculations, I wanted to get into a little bit more depth of what happens when you titrate a strong acid with a strong base. So as you perform a titration, you can actually graph the pH as a function of the volume of base that's been added, right? And what you'll see is you get this very characteristic S-shaped curve. But this is called a titration curve. And so you'll notice that the pH doesn't increase constantly as the volume of base is added, right? Originally, the pH doesn't change very much. It's like almost flat. It's not changing all that much. And then when you're near 7, the pH like skyrockets. It jumps up very quickly, and then the curve kind of flattens out again. And this is kind of a function of the fact that pH is measured on a log scale, so it's this non-linear scale to begin with. And when you're near the equivalence point, the concentrations of H plus and OH minus are very close to each other, and that causes the pH to change more rapidly, which is kind of funky. But it gives us this nice looking curve. Let's see if we can actually calculate out the pH at a couple of different points in a titration. So we've got 50 milliliters of this 0.1 molar HCl solution, which is being titrated with, we can't see it, it's a 0.1 molar sodium hydroxide solution. I want to know the pH of the solution before we add any base, after we add 10 milliliters, at the equivalence point, after 55 milliliters. And these are example calculations, but theoretically, we could calculate the pH for literally any amount of base that's been added, and we could actually like plot out a titration curve if we wanted to. So go ahead and pause the video. Try to do it on your own. At least do part A on your own. Then you can watch. Then you can pause. Then you can watch. Then you can pause. Then you can watch. But do each part on your own because this is like really good practice. Cool. Before any base has been added, it's always helpful to write out your equation for what's going on. Before any base has been added, if we're just calculating the initial pH, the concentration of H plus is just going to be equal to the concentration of HCl, right? And so this is a fairly straightforward calculation, right? To get the pH, you just take the negative log of that. That's 1. After some base has been added, things start to get more complicated. So let's look after we've added 10 milliliters of base. We're going to have to figure out the number of moles of H plus that was originally present, the number of moles of OH minus that we've added, and then based on that, we can calculate the moles of H plus we have now in order to figure out the pH. So to get the moles of H plus that was initially there, where we do the moles, the volume times the molarity, right? And of course you have to divide the volume by 1,000 milliliters to get the moles. To calculate the moles of OH minus, same idea, right? So we're doing the volume, of course, divide by 1,000 to convert it to liters, and then using the molarity, right? So we've got 0.005 moles HCl and 0.001 moles OH minus. Cool. Okay. Now, what we want is we want to know the pH now, which means we need to know the concentration of H plus now. The HCl and the OH minus are going to react with each other and form water. So however much OH minus we add, the H plus, that much H plus is going to get used up reacting with the OH minus, right? And so 0.001 moles of OH minus is going to neutralize 0.001 moles of acid. And so we're going to end up with basically subtracting out that many moles of acid. So we're going to end up with 0.004 moles of H plus that's left over, right? So that's the amount of H plus we now have in our beaker. Cool. We can almost calculate the pH. We can't yet because to calculate pH, we need a concentration. This is just an amount of moles. not only did the moles of H plus change, the volume of our solution also changed, right? We had 50 milliliters, we added 10 more milliliters. And so we've reacted away some of the H plus and we've increased the volume. So kind of like for two different reasons, decreased the concentration of H plus. So we need to figure out the new volume, right? It's now 60 milliliters instead of 50. We're gonna have to divide the moles by this in liters, of course. Right? So we're dividing the moles by 0.06 liters to get a molarity of 0.0667 molar. Take the negative log of that to get the pH. We've got a pH of 1.176. So notice that the pH actually hasn't gone up too much, which kind of matches what we saw on that titration curve, right? Originally the pH doesn't change too much, and then it like changes a lot all of a sudden. Cool. At the equivalence point, if you're titrating, and in any titration, right, the moles of the acid is going to equal the moles of the base at the equivalence point. So that means that the only thing that's present, essentially, is the anion and cation that like came from the acid and the base, the conjugate acid and the conjugate base. In this case, we were reacting a strong acid and a strong base. So the conjugate of a strong acid, Cl minus, is essentially like not basic at all, right? HCl is such a strong acid that its conjugate base is actually just not a base. It's like garbage, right? So Cl minus does nothing. Same with Na plus. NaOH is a strong base. Its conjugate acid, Na plus, is so weak that it's not even acidic at all. It's neutral. So both of these ions are neutral. Neither of them impacts the pH. Meanwhile, the H plus and the OH minus have both reacted together to make water. So we've got essentially no H plus and essentially no OH minus. Of course, we have like 10 to the minus 7 of both. But we've got two ions that don't impact pH, and so we're going to end up with a pH of 7. So if you're titrating a strong acid and a strong base, at the equivalence point, your pH will be 7. That's not going to be true if either of these is weak. Right? If either of these is weak, then the conjugate is going to have actual acid-base properties. The conjugate is going to not be neutral. And so your equivalence point actually won't be at a pH of 7. It will be at some sort of other pH, depending on whether you're reacting a weak acid or a weak base or both. But for a strong acid, strong base, the pH at the equivalence point is just 7. Cool, okay, so for part D, let's calculate the pH of the solution after we've passed the equivalence point. Right, so we've added 55 milliliters. We've added more base now than we started with acid. Cool, again, you're gonna wanna know the moles of H plus and OH minus that were added, and then you'll wanna figure out how much is left over in your beaker after they've reacted. Right, so to calculate the moles of H plus present, that's actually the same as the calculation from before, right, because we haven't changed the amount of acid that we started with. To calculate the moles of OH minus that we've added, we can do the same type of calculation, but we'll get a different answer, right? So we've added now 55 milliliters instead of just 10, right? Convert that to liters, and then use the molarity, right? Multiply that by the molarity of the base to get the moles of base. So we've added 0.00550 moles of base. So now we need to figure out the moles that are remaining. In this case, we've added more base than acid. Remember, any acid that's there is going to react with any base that's there. The acid and the base will completely neutralize each other, right? That's a very exothermic, very product-favored reaction, right? It goes to completion. And so the 0.005 moles of acid is going to completely react and use up that much base. And so we're going to have leftover 0.0005 moles of base because all the rest of it got used up. That's how much we have left over. Okay, so once we know the moles of sodium hydroxide, we're going to need to know the concentration. In order to know the concentration, we actually need to know the volume, right? So we started with 50 milliliters of acid. We've dropped in 55 milliliters of base. And so we're ending up with 105 milliliters, which you'll want to convert to liters, right? So that's 0.105 liters. Take the moles, divide it by the volume to get the concentration, right? We get a concentration of hydroxide of 0.048 molar. with only 2 significant figures, because this number following the subtraction rule has only 2 sig figs. Now we take the negative log of that. That gives us the pOH, which is 1.3, and then subtract that from 14 to get a pH of 12.7. Cool. Let's take a look at the last part of this question. So the last part of this question is asking us to identify all the species present in the reaction mixture in all 4 parts. They really mean present in non-negligible amounts. Before any base is added to the acid, we're starting with an acid solution. We're gonna have H+, and we're gonna have Cl- in our beaker. Of course, there's water for all the parts. And then technically there is also some OH-, but it's an incredibly small amount, right? The pH is 1, that means the pOH is 13. So there's a concentration of 10 to the negative 13 OH-. That's negligibly small. So essentially in scenario A, we've got H+ and we've got Cl-. Those are the only ions that are present at any noticeable amount. After we've added 10 milliliters of NaOH, well, the OH has all reacted with the H+ from the acid. So there is no OH- in scenario B. We've dropped in a bunch of Na+, and that's a spectator ion in that chemical reaction. So we've got a bunch of Na+ floating around our beaker. We've got a bunch of Cl- from the HCl, and we still have an overall acidic solution, so we've still got a bunch of H+. So we've got Na+, Cl-, and H+ floating around. But we have no OH- because it's all been used up reacting with H+. At the equivalence point, the H+ and the OH- have both been used up, right? They've both reacted completely with each other because we have exactly equal amounts of acid and base. So at the equivalence point, we've got no H+ or H-. All we've got is Na+ and Cl- floating around. And then, of course, technically, right, we've got H+ and OH- in a concentration of 10 to the negative 7. But essentially, we've just got Cl- and Na+ floating around in our beaker. After we go past the equivalence point, we've still got Na+, we've still got Cl-, we've also now got a bunch of OH- as well, right? Because we now have a basic solution. Cool. It's worth noting, at no point would we ever have H+ and OH- in any non-negligible amounts, right? H+ and OH- always react together to make water, right? The maximum amount you're gonna have of both of them at the same time would be like 10 to the negative 7 if you're at a neutral pH. As soon as one goes above that, the other goes below that, right? So essentially you're always gonna have these really, really tiny amounts of one or both of H+ and of OH-, right? If you're in an acidic solution, you'll have H+, but you won't have OH-. The OH- will be used up reacting with H+. If you're in a basic solution, you'll have OH-, but you won't have H+. The H+ will have been used up reacting with the OH-. Cool. So just to return to our titration curve, right? So we're graphing pH versus volume of sodium hydroxide added, right? You can see the equivalence point right here in the middle is where the pH is 7. And in this case, if you're titrating with equal concentrations, the equivalence point happens when the volume of NaOH added would be equals the volume of HCl, since they're equal concentrations. Before you hit the equivalence point, the pH depends on the amount of H+ that hasn't been neutralized, right? That's what we did in our calculations. We calculated the leftover H+ that hadn't gotten neutralized. Past the equivalence point, your pH is going to depend on the amount of extra OH- that you've added, right? The amount of OH- in addition to the amount that it took to react with the H+. And of course, at the equivalence point, if it's strong acid and strong base, your pH will be 7. We talked briefly at the beginning about how the equivalence point and the end point aren't the same. That's because the indicators that you're using don't actually change color at a pH of 7. The most commonly used indicator is phenolphthalein. Phenolphthalein changes color at a pH of around 8 to 9. And so you've actually, if your phenolphthalein has changed color, you've actually overshot your equivalence point. That said, the blue dots here are representing drops added. the phenolphthalein, to go from the equivalence point where the volume of base equals the volume of acid added, to go from that equivalence point to the end point where the phenolphthalein changes color generally takes only about 1 drop, because the pH changes so steeply when you're near the equivalence point. So approximating that endpoint and saying, okay, at the endpoint, the moles of acid equals the moles of base, that's a pretty good approximation, right? In reality, you maybe have added 1 drop more of base than the amount of acid, but you're pretty darn close to having moles of acid equal to moles of base. The other indicator that's used frequently is methyl red, which changes from red to yellow at a pH of around like 5-ish. Again, that's fine, right? That's a pretty decent indicator to be used in a strong acid, strong base titration, because it's changing color about 1 drop away from the equivalence point. Cool. The last thing I wanted to mention today is, let's take a minute and think about what the titration curve would look like if, instead of dropping base into a beaker that started with acid, let's imagine we have a beaker that started with base, and we're going to drop acid into that beaker, right? Strong base, strong acid still. You're going to end up with a titration curve that looks something like this. So it's going to look pretty similar to the titration curve we had before, but if you're starting with base, then you're going to start at a high pH, and the more acid you add, the pH is going to go down lower and lower and lower. The shape of the curve is still going to be the same. So you're still going to have this kind of S-shaped curve, although now it's like a backwards S, because like it's starting up there and going down there, right? So I guess it's like a Z, a kind of like awkward Z-shaped curve. Anyway, you still have the same shape other than it being like flipped. And the pH still changes very rapidly around the equivalence point. The only difference is now we're starting at a high pH and going to a low pH. All right, folks, I hope that's been helpful. The titration curves actually are not on this year's AP exam. That's part of the topics that have been cut, but titration and the titration equation is on this year's AP exam. And, you know, it's basically just stoichiometry. It's just a specific example of stoichiometry. So that is on this year's AP exam. And then the titration curves is just a nice little application of that. We'll talk a little bit after the AP exam about titration curves for weak acid and weak base titrations, which are kind of interesting and a little bit differently shaped. But we'll hit that after the AP. This week, we're going to talk about a couple more topics that are on the AP exam, which is some really basic redox chemistry. That's another unit that's mostly not on the AP exam, but there's a little bit that is. So we'll talk about that later in this week. So I will see you then.